Okay, so let's compare nuclear reactivity, which is what determines the critical mass of a material. Weapons-grade plutonium has a bare sphere critical mass, so sort of a ball of it sitting on the table by itself, of 11 kilograms. You don't want to have more than 11 kilograms. You don't want to have 11 kilograms of this stuff in a sphere because it'll quite honestly go bad on you very quickly. Now, reactor-grade plutonium has a bare sphere critical mass of 13 kilograms. So it's only about 20% more of it required to make a critical mass. And you'll note here down at the bottom that highly enriched uranium, which we know is good for nuclear weapons, has a critical mass of 56 kilograms. And so both reactor grade and weapons grade are a lot better, about 4 to 5 times better than highly enriched uranium for making a nuclear weapon. So the lower the critical mass, the less material you need per weapon. Next view graph. Okay, now there are 3 ways to cause a nuclear explosion. You can increase the mass of fissile material above critical for that element. And that's because the more atoms you have clustered together, the more likely it is that a neutron is going to cause a fission before it escapes from that mass of material. And so increasing it with uranium-235, you can build something like Little Boy, where you just put 2 slugs of this stuff together to make a critical mass. You can't do that with plutonium. You can use a fissionable material with a higher fission cross-section, like plutonium-239, and therefore you have a smaller critical mass to cause the explosion. And third, the way most weapons work today in the world, you can compress a subcritical mass of fissionable material, typically using high explosive, implode it, it's called, and you move the atoms closer together and make it more likely, because they're closer together, that a neutron will hit and fission an atom by imploding a mass of fissionable material. Have the next view graph. So sort of looking at that in a cartoon format here, the little blue balls are supposed to be atoms. The neutron is that arrow. And if you don't have enough atoms, you don't have a critical or a supercritical mass of material, the neutrons will escape before they cause a fission chain reaction. But if you get a lot of those atoms clustered together in a supercritical or a critical mass, the neutron can't avoid hitting and causing a fission chain reaction before it escapes from the material. Next view graph. So reactivity, continuing here. I'll try to be generous here rather than saying it's disinformation. There's a misunderstanding in the technical community about the utility of plutonium-240 in nuclear explosives. Now, the reason presumably is because plutonium-240 has a negligible, a very small fission cross-section with slow neutrons. And slow neutrons is what drives all power reactors. That's why there tends to be water in power reactors or graphite to slow the neutron down in order to have a nuclear reaction going on. And so actually, if you add, as the plutonium-240 in a reactor, as it burns up its fuel, accumulates, it actually slows down the reactor. And so a reactor engineer who doesn't understand nuclear explosives might think that plutonium-240 is not useful for explosives. However, it is a very good explosive fissile material with fast neutrons. And fast neutrons are what drive nuclear explosives. Next view graph. Now, all of the plutonium isotopes that I've listed are fissile for fast neutrons. You can see the critical masses here, 10, 238, 239, 10, 240 is 40 kilograms critical mass. And you can compare that to 235, uranium-235, which is a very good bomb material, which has a critical mass of 56 kilograms. So all of this stuff works quite well in a nuclear explosive. Next view graph. And the reason, this is a little technical here, what I've got plotted on the vertical axis is fission cross-section, so if you will, the reactivity of the isotope. And I've plotted the isotopes separately here, and across the bottom, incident neutron energy is basically whether it's a fast or slow neutron. So down at point 1, you can see the green line is 240 and the blue line is 239, the good stuff. And clearly the reactivity is very, very poor for 240 for slow neutrons down at point 1. However, up where a nuclear explosive works, up around 1 here on the horizontal axis, the green lines and the blue lines almost converge. They're very close, they're negligibly different. And so 240 is almost as good as 239 for a nuclear explosive. Next view graph. Okay, fission cross-section. This is a physics metaphor here or analogy. A higher cross-section material appears bigger, if you will, to neutrons than a low cross-section material. And so in an assembly are more likely to intersect a neutron and fission than a low cross-section material.